hello again. I just realized that lots of times you want to know how fast things go. Like, how fast can you walk? How fast can you run? And especially with these sneaky little waves, how fast do they go? And how do you measure that? So if you want to measure how fast you can walk, one way, of course, is to walk a distance and measure the time. But it's not always easy to do that, especially with waves. So if you wanted to measure how fast you can walk, what if you just said to yourself, how many steps do I take per second or per minute, and how long is each step? And that's what you do when you try to measure the speed of a wave, because a standing wave, you sit there and you look at it. John made that nice standing wave, and it's not moving. It looks like it's not moving. It's not going anywhere, and it's basically the reflection of two waves going in opposite directions. And so it looks like it's standing still. How would you measure its speed? Well, you do it by measuring the length of a step, which is called a wavelength. And you take the wavelength, and then you say that's how long each step is, and then you take the frequency, and that's how many steps that the wave makes in a second. Remember, a hertz is the word we use for cycles per second. So if you shake your hand 3 times a second, that's 3 hertz. If you have a radio wave and it's 107.5, that's 107.5 million cycles per second, or megahertz. That's a pretty fast wave frequency. Light waves are times 10 to the 14th, so they're huge wiggly frequencies. But we're going to look at waves that we can actually measure the speed, and we have a little machine that shakes the wave. It makes the wave, and then it makes a standing wave on a string. And you can measure the frequency, and you can measure the wavelength. So let's look at the wavelength for a second. If I have a string, and it goes from, I'm going to do it backwards, if it goes from here to here, and I take the string and I shake it, and this string has got some vibrator on this end, and it's got a fixed end on this end, so it sits there still. And I shake it, and I make it make, let's just do 2 wavelengths. 1, 2 wavelengths. Okay, so a wavelength, I hope you can see this, a wavelength is 1 wave. And this thing's vibrating, so half the time it's up and half the time it's down. And that's kind of my best picture, and I hope that you can see it. So one instant it's up here, the next instant it's flipped, and it's going back and forth, and these little points where it's still are called nodes, and I think you saw that in the video from James Dan. So a wavelength then would be from here to here, and physicists are so lazy, they don't want to write the whole word wavelength. So they just use a little letter that looks like a guy walking just a little bit. It's called lambda. Hello, pen. Pens don't like to write. But anyway, the wavelength is called lambda. It includes 2 loops of the wave. So my string here is 2 wavelengths long with this wavelength. And now if you look at the little box, the little meter on the wave driver, it's going to tell you how many cycles per second we're doing. So let's just suppose that the cycles per second says 10. 10 hertz. Why not? I made it up. 10 hertz. And the wavelength that you now measure, let's just say this is 20 centimeters. Okay, so now we have the frequency, which we use the letter F. Frequency, come on F, my pen doesn't want to write. But the frequency is 10 hertz, and the wavelength is 20 centimeters. So what's the speed of this wave? Well, the 10 hertz is how many steps you take every second, and the 20 centimeters is how many centimeters you go in every step. So if you multiply them together, you have steps per second. Steps don't count, but steps per second times centimeters per step. And so if you write that down, you're going to get, let's see if I can do it from this side and see what happens. You're going to get the wavelength times the frequency is the speed. And so the wavelength is 20 centimeters per step. The step is kind of a fake unit. And the frequency is 10 steps per 10 steps per second. Unfortunately, steps and seconds start with S, so you've got to be a little careful here. Write it out. Anyway, 20 times 10, I can even do that myself. 20 times 10 is 200. And I hope you'll see this. You will, I think. Now I'm going to grab a different pen. Forgive me for the crudeness. 10 times 20, I can even do. The V, the speed, is 200 centimeters per second. And that's the only formula you need for doing the waves. Wavelength times frequency equals speed. And if I can get you to remember to put units on everything you do, then you can look at it. And you've got 20 centimeters per step and 10 steps per second, okay? And the combination of those two gives you centimeters per second. And that's the speed. So wavelength times frequency is speed. Okay, that's a good start on this one.
Okay, so here's the experiment part of the lab. Here our goal is going to be to find out the speed of a wave on this stretched bungee cord. One way we could figure out the speed is I could tap the cord here and I could try to take a stopwatch and see how long it took to get to the chair on the other side. But you can see, unlike the rope, it's so fast that there's no way I could do that. So we're going to use the nice equation that Sue showed you about getting the speed by multiplying the wavelength times the frequency. So we're going to make a standing wave, and I have the function generator here. This is a thing that's going to drive this speaker. The speaker has a post on it, and when I drive it, it's going to go up, move this up and down like that. And I can control the frequency. So if I turn this on, it's moving this thing up and down. And we're not getting much of a wave, right? Of a standing wave, because the reflected waves are not syncing up with the incoming waves. So I'm going to look for the place where the frequency is just right. And there, it looks like I found it. Now I'm getting a jump rope wave. That's at about, if I look at the power supply, it says that is 6 Hertz, which means this thing is going up 6 times every second. So there's our frequency. And now what's the wavelength? Well, we remember that the wavelength is an up and a down, right? And so this, if I were to freeze it at any one time, it's just going up and down and up and down. So a wavelength is going to be 2 of these. It's going to be an up plus a down. So this is really just half a wavelength. And how big is it? Well, I can get my tape measure. I have a tape measure. It's in centimeters, and I'm going to measure the length, and it says 150 centimeters. So the length of this rope is 150 centimeters. So what's the wavelength? Well, if the wavelength is 2 of these humps, then the wavelength has to be twice as big as this. So it has to be 300 centimeters. Okay? So what you're going to do is write down these numbers, and for each pattern, you're going to have a wavelength and a frequency, and if you multiply those together, you can get the wave speed. And we're curious to find out what the wave speed is. And we're also curious to find out whether the wave speed changes if I change the frequency, or is the wave speed some kind of constant that is permanently a property of this particular string at this particular amount of tension. So that's our two questions. One, what is the wave speed? Two, does it change as I change the frequency of the oscillating thing, okay? So numbers, so I'm going to start changing this. You write down numbers. So first of all, we have a frequency of 6 hertz, 6 cycles per second. And remember that this string is 150 centimeters long, so I'm going to let you calculate the wavelength from now on. This one we said was 300 because this is a half a wavelength. Okay, and I'm going to always keep this length 150 centimeters. Okay, let's find the next situation. We're going to call that this we call the first harmonic or the fundamental. So if I increase the frequency, you see we get back to kind of randomness that doesn't do much. It's not. And then I'm going to go a little bit more and I'm going to look for that. And there we go. So now I have a frequency of 12 hertz. And what is the wavelength? Okay, remember the length of the string is 150 centimeters. And if we were to freeze it right now, we'd have an up and a down, right? So, okay, here's another one. I'm going to keep going. And looking for that nice, there we go. Now I have 3 humps. And that is a frequency of 18 hertz. What is the wavelength? So write down the wavelength and the frequency. Remember the whole thing is 150 centimeters. Okay, so I'm going to keep going. What's the next one? There we have 4. Remember that's 2 wavelengths, right? Just like with the rope. Okay, the frequency there is 24 hertz. Okay, I'm going to keep going. Now I have a frequency of 30 hertz. And 1, 2, 3, 4, 5 sections, 5 half wavelengths. Okay, I'm going to go one more. That's 36 hertz, 36. And you can count the number of things. I'll help you. 1, 2, 3, 4, 5, 6 sections, or 1, 2, 3 wavelengths in 150 centimeters. Okay? So you go ahead and make a chart, multiply all these frequencies times their corresponding wavelengths, and see what you get for velocity. Your velocity will come out in centimeters per second, and it won't be exactly right, exactly the same every single time, but will it be close enough that you think that the speed doesn't change no matter how I change the frequency? Or will it change enough that you say, yeah, it does, the speed does change when I change the frequency? Okay? And if you get your answers of velocity in centimeters per second, I encourage you to try to convert those somehow with Google or whatever to miles per hour and see if it makes sense, right? We noticed that the waves traveled really fast on the string. So maybe make a guess on how many miles per hour you think that wave is traveling. And then when you get your centimeters per second number, see if you can convert that into miles per hour. You could ask Google or something and see if does it make sense? Does it come close to a really fast speed you thought it might be? Okay? Okay, so here is another example, more of a real world example. Instead of a bungee cord, I have banjo strings, and if I pluck a banjo string, then it's going to vibrate up and down just like a jump rope, like on the bungee cord, but the vibrations are so small you can't really see them. But if we imagine that it's jumping like a jump rope, we can figure out the wavelength, because it's going to go have a node here and a node here, and we can think that this must be a half a wavelength. So if we measure this distance, then we can tell the wavelength is going to be twice whatever that is. Right? Can we get the wave speed from this? Well, if we know that, we figured out the wavelength like that, how can we get the frequency? Well, I have a little frequency meter here on my phone, so if I pluck the string we can see what the frequency is. And it says it's about 120 Hertz. Okay, now I'm going to do one more example where I'm going to make the string half as big by putting my finger here, and now I'm going to pluck the string and it's going to be half as big, and you'll get some more numbers that you can use to calculate the wave speed and see if the wave speed is the same or different as it used to be. Okay, you make a prediction and we'll see what happens. Okay, ready, predict. Did you predict? Okay, here goes. And it's just, turns out it's just about twice what it was, yeah? And if you want to try to calculate the speed of the wave on this string, I will give you the distance here. It's 70 centimeters. So you can take 70 centimeters as this. Remember, the wavelength is going to be twice as big as that because only a half a wave fits. And see if you can, from the wavelength and the frequencies, get the wave speed. It's going to be pretty fast. Is it faster than the speed of sound? What do you think? Try it out. Okay, so that's a very practical example of standing waves. Pretty much all musical instruments use standing waves, even if they're flutes and trumpets or stringed instruments. Here's another example. Remember we saw that with the rope, if I stretched it tighter, that the wave traveled faster. So on a stringed instrument, we have these knobs to stretch the strings tighter. So if I turn this so it gets tighter, we saw that the speed of the wave should travel faster on a tighter string. And if it travels faster, that means it's going to have a higher frequency. So let's see if that happens. I'm going to turn it up. Hear that higher frequency? A higher frequency to our ear sounds like a higher note. And I'll go back lower. So we're going to have a whole lab about musical sounds and frequencies next week, so hope you stay tuned.
Here we go again. That last video I made was going to be a test video, but I liked it, so I decided you get it anyway. That was the one on wave speed, where we have wavelength times frequency gives you the speed of a wave. And I hope that made sense after you saw all the demos. So right now, this is the end of your lab, and I'm going to talk a little bit about resonance. And I got invited once to give a talk on anything I wanted in physics to a bunch of people who were taking a course called Spectrum. One lecture from each department all over the campus. It was a pretty cool lecture system. And my talk was on resonance. And so what is resonance? So I'm guessing that you've all pushed a kid on a swing at some time in your life. And when you push a kid on a swing, you have to push at the right time. And if you push at just the right time, each time you push, the kid goes a little higher. And that's a situation where don't go to sleep and just push any old time because it won't work. Sing in the shower. You sing along, and some sounds are just really louder and more brilliant than others. And that's when you hit the resonance of the shower. The shower likes that particular frequency. If you have a Coke bottle, I should have one here and I don't, you go if you blow it just right. That's when you set up a resonance wave inside the bottle, and it makes what we call a resonance, and you make the sound. And other frequencies that you blow across don't work, so you learn that. You can take a little radio in your hand and you can tune it and you can pick up all the different stations. And that's because each station has its own frequency, and when the radio is set to pick up the frequency of a station, like good old 107.5 KPIG or some other station, then the resonant circuit picks up just that station and it ignores all the other stuff that's out there. And if you haven't thought about it, the world is just absolutely full of radio waves and TV waves and all the other kinds of waves. And that's part of today's lab in a way. Anyway, interesting thing is if you watch the tides, they come and they go and they slosh back and forth, and they're kind of pulled by the moon and they're pulled by the sun. And they go up 3 or 4 feet most places, and they maybe go up a lot more in some places. There's a place in Canada called the Bay of Fundy where the tides are 30 feet high, I think. Don't quote me on that. Anyway, the cool thing about the tides is it's a sloshing of the ocean in the ocean basins, and it is driven by the moon and the sun. And here's the good thing. It's not resonant. If it were resonant, it would be like sloshing back and forth in the bathtub. If you go at just the right speed, you can get the water all over the bathroom. It's really a good thing that the tides are not resonant with the sloshing of the oceans in their basins, because if they were resonant, we would get huge tides and we would never want to live on the coast at all. So anyway, resonance is really cool. I've got a little wood lathe in my garage, which is kind of my hobby. And what it does is it spins a hunk of wood. And as you speed up the speed, you start it going slowly because a hunk of wood is kind of lopsided and it wants to shake the whole thing. And you get to a place where the lathe is just shaking. And then you go just a little beyond that and it stops shaking so much. And that's where you end up using the lathe, usually just a little bit past that first resonance that you hit, where the lathe trembles because of the off-center shaking of this big piece of wood. So that's the concept of resonance. Now, all the standing waves that you saw were situations with resonance. When you play a musical instrument, they operate on the principle of resonance. You get a whole lot more sound out at a particular frequency depending on which string you're plucking, or the vibration of the face of maybe a violin or something. All the musical instruments that we'll see next week are based on the principles of resonance. Your own voice has resonant frequencies, and next week you're going to see what it looks like when you hum and sing, and you will see that when you say something, your voice puts out a frequency that matches the shape of the inside of your lungs and your throat, and that's why your voice is different from all the others. It's amazing. Voices are at least as distinctive as fingerprints. So we're going to talk about resonance a little bit more next week. And this week, I hope you enjoyed learning a little bit about waves, standing waves, resonance. And what are we trying to do today? What's your job? It's in the email. You need to watch the bunch of things that John and I have set up for you for this week's Waves Lab, and make some notes, and please put your name on every sheet so that when I'm looking at them I don't go, who was this again, and I have to go back to your email. So put your name on every sheet. Give me a bunch of chicken scratching notes that you made while you were watching this stuff so that I know you did it, and answer the quiz that I sent you on email, and get that to me hopefully by next Thursday, when we're going to start the next lab, which will be music and noise. And take good care of yourselves. I really miss being in lab with you, but seems to be that's where we're at right now. Okay, I hope you're doing all right. Bye-bye.